Let's get rid of that. Hi, so I'm Simon, and I work in a site reliability engineering team at NVIDIA. There are quite a few. And one of the things I was asked to do about a year and a half, 2 years ago, was to try and figure out some storage for Cambridge-1, which is a supercomputer that NVIDIA operates in the UK. I feel like a fraud too, because I'm not actually a Lustre expert at all. My job is essentially to be dragged in to look at various pieces of infrastructure and to try and turn them into software. Sometimes this works out quite well, sometimes it doesn't, to be honest. But I'll let you decide for yourself with this one. So Cambridge-1, NVIDIA call these superpod. It has compute in it. The interesting thing about this one was that lots of life science providers came in, and they would come for a few weeks, maybe a couple of months, and then they would leave. And so we had to worry about multi-tenancy and how to try and keep their stuff separate from each other. And my job usually is to do with storage. I'm that sort of SRE, and so I was asked to try and figure that out with some other people. And so in a multi-tenant system, usually, the network is a pretty good place to start. So Slurm's got this concept of partitions that's quite useful. But one easy way to do it is you've got your nodes. So in particular, we're interested in here, how might I take a compute node and shuffle it from one partition into another? And the network is always a good place to start. Obviously, the compute plane has a concept for partition, but the network is important. And if I can isolate that off, there are going to be several networks involved. Certainly, there'll be a network for storage, others for management, compute. Then I can do that. And so one way I could do the storage is by having lots and lots of Lustre file systems all on their own separate little networks, and then I switch around, switch ports and ACLs and all this other stuff. But we didn't want to do that because my job essentially is to try and treat it a bit more like software. So I really want to test it. I don't want, ideally, to be in a situation where I have to reach out to an API on a switch or a router somewhere. And this is also one of the reasons why we didn't go with Kerberos. It's not because it's not great or even better than this. It's because we wanted to be able to take what we produce and then try and reuse it and test it. And we didn't happen to have a spare supercomputer to do that in. So we're interested in keeping things as small and simple as possible. So what we wanted to produce in the end was an API for tenants and an API for nodes. So for tenants, I have a tenant come in, I'm going to put a REST API over it, I need to create it, I need to delete it, might need to read it and update it possibly, and then for nodes, I need to assign those to tenants as well. So I need some endpoints to deal with tenancy of each compute node as tenants come in and go and as their nodes move around. And again, I really want to try and not reach out to stuff around me if possible, because infrastructure is difficult, and every time I reach out to someone else and depend on someone else or depend on anything else, it is hard for me to test that. So I prefer not to where possible, or sometimes, you do. And so we know what we wanted to do, and then we actually had to go and do it, which was the interesting bit. So one of the things we wanted was multi-tenancy within a single Lustre file system, and Lustre obviously has some concepts that are quite nice for that. So we end up quite simply, so there was a very good talk earlier about Kerberos. We're also using GSS. We went with SSK keys. And the reason we went for those is because we didn't want to have to worry about an external Kerberos. We wanted to keep everything black box and present an interface over the top. But before we could get to that, we had to be able to isolate storage. Obviously, you've got the file set in Lustre. That's quite nice. And then you have to associate that with a node map. So the thing about the node map is that the NID isn't strong enough. So my host has a NID or several NIDs, and I need to assign those NIDs to the node map in order to actually assign that file set to any given mounting node. But the NID isn't a particularly great source of authentication because it can be trivially spoofed. If I've got root on a client node, I can just say, well, great, I'm this guy, give me the storage. And so obviously that isn't good enough. So we put SSK over the top, and when any RPC, a mount RPC being the most, the simple example there, I come in, and if my SSK key matches a node map, then if my network identifier, my IP address, if you like, is in that node map, then I can mount the storage. So that was auth. For isolation, so because we're already using GSS, one way we can stop ourselves from reaching out to other things around us is to use encryption, obviously, but that's got a horrendous performance penalty. So no one wants that, least of all us. But the nice thing about InfiniBand is that it does have limited and full membership, which we tried it out because we weren't sure if it would work, to be honest, and it turned out to work okay. So in an InfiniBand partition, we weren't keen to go and reassign P keys. One way that people sometimes do this is they reach out to a Mellanox API, for example, and they say, right, well, change the partition membership of this node. So it's talking to a different piece of storage. In this case, we didn't have to do that because if you give full membership to a member of a network in InfiniBand, it can see anything, it can talk to anything within that network. If you give it limited membership, it can only see the full members. And so for us, because our mounts are authenticated, that worked out quite well. There's no moving parts. So we quite liked that as a solution. We stuck with it, and that was our isolation. And then we had the problem of actually having to automate it. And so again, we're going to gun for two APIs here. We want one for tenants. We're going to do REST because it's simple and everyone understands it. And then we want another one for node lifecycles within those tenants. And we had a deadline. I'm no C hacker. And the idea of trying to write secure C code in the time we had was not very appealing, if I'm honest. So we just took the MGS, which is a convenient way to do this, and we're literally running commands using LCTL and other commands on the boxes ourselves. So that's what our APIs are using under the hood. For tenants, that was actually quite straightforward. So one of the things about creating this node map and this file set and this SSK that we're using, that's what a tenant is to us. We bind all those things together and we're trying to make it simple to anyone that consumes our software. It takes quite a long time to spin up, so particularly the SSK takes potentially several minutes to generate, and that's not great because we don't want that time attached to any API call. So instead, we just make it asynchronous. We have a reconciler process that runs very close to the MGS. And whenever someone tries to create a tenant with our post call here, we drop a simple little state marker in, and the state marker exists alongside others. The reconciler sees the state marker, and then it tries to ensure that state is there slowly and in its own time. So it goes through, it updates any file sets that need to be created, creates any SSK keys, sets up any node maps. And conversely, the same needs to be true for deleted tenants as well, because obviously I need to clean this stuff up. So if someone comes in and blows a tenant away, we put another state marker down saying that they should be removed, and then the reconciler slowly comes in, removes any file sets, removes any SSKs, cleans up for us. So that was fairly easy. The nodes were slightly more interesting. And one of the reasons they were slightly more interesting is because we had a time limit. So in the design parameter, I should say this is an original version of Cambridge-1 I'm talking about. There have actually been two, and this is a Slurm-based compute. And when the nodes switch into a different partition, which happens in this case through the Slurm epilogues and prologues, we were given in the design a limit. We have to be able to move our nodes within a certain time frame. So you have to try and be fast. Right? And the reason this was tricky was because when we were using LCTL to control the membership of these nodes, I'm trying to add a host to a node map to a tenant. If you have a REST API, then it is in principle possible to have very little time between these calls. If you want to see a line you're typing, obviously there's a time delay. But if you've got an API, I potentially have lots of these adds and deletes. I've got host 1, and I'm trying to add it to a node map. This might happen many, many times very, very quickly. When I do that, my ordering isn't guaranteed. If I add a node to a node map, and I quickly remove it, and if I do that fast enough, and this isn't a flaw in Lustre, I think this is very much part of the design, I don't know for sure if that node is in the node map or out of it when my last API call completes, which if you're writing a security API is a bit of a problem. So what we then discovered, perhaps predictably enough, was that if you then poll it, so I add a node and then I use something out of band like LCTL get param to check it's there, then I can then safely delete it. My last operation to go in will be the state, very likely, of the node map at the end. So that's great, except that it's slower, not fast enough. We did discover one other thing, though, which was quite nice, which was that as long as you can keep the NID ranges independent of each other, so I've got two hosts, say, and I add very quickly host 1 to a node map and I remove it, and I take host 2, I can have these operations run in parallel. So as long as the NID ranges don't intersect, I can go as fast as I want across machines, but I have to go slowly for individual ones. So we're able to use that to just about make our speed requirement. If you imagine you've got three operations here. In the first operation, we're going to add host 1 to a tenant, to a node map. And it's going to be enqueued with a hash. So basically, we're going to chuck this in a queue for host 1. That add operation hasn't been done yet. We're going to action that later. Then a few milliseconds later, we have another operation, and it's going to be a delete for host 1. So what we did here was we simply enqueue the delete behind the add, because we need that add to complete in order to make sure that our ordering's good, and we don't end up with an unexpected state. Then in the third operation here, which I'm in the way of, we're going to add host 2 to the same tenant, to the same node map. And we found that if we chuck that into a separate queue, that worked fine. What's going to happen here is that host 1's going to be a bit slower, because the delete operation will have to wait for the add to complete. But with host 2 here, I can at least run that in parallel. And that was just about fast enough. So got away free with that one. Okay, so just to recap, so for tenants we used node maps, file sets, SSK keys, and we wrote this reconciler process that handles all this stuff in the background for us. It sounds complicated, but there wasn't actually much code to it. And then for node isolation, we ended up adding and removing these network identifiers, the NIDs, from the node maps. And we needed queues to do that because when we put an API over it, potentially with the 80 nodes in the data center, there was a little bit more traffic than it could safely handle. And we put a REST API on the top. And what we ended up with was a system that looked somewhat similar to this. So there's some tenant administration over there. That could be software, it could be people. To be honest, I don't really care because that's why I wrote an API. I provide an interface and then someone else generally consumes it. And then in the interface itself, we have the post and delete tenants. So we can create and remove tenants, which are just node maps from this system. Those are going to come as state markers. So both of those just drop some state here that the Lustre reconciler sorts out in the background, just endlessly cycling around and trying to make sure the node maps and SSKs exist. And then finally, we had the NIDS call, which works very differently to the others. So when I'm trying to add or remove a host from these node maps, I need my queues. Otherwise, my ordering gets messed up, and that's problematic for us. And then finally, we had the only other part of this was the isolation. So you've got your compute nodes over here, one's in tenant A and B in this case. And yeah, to do the we need to make sure that the data in flight definitely can't be seen from one tenant to another, obviously. So we just use limited and full membership and the InfiniBand partition for that. That's it. When we'd finished, there were a few things that did occur to me. So one of them was about the way in which authentication works for node maps. It did occur to me that perhaps if you've got a GSS API method, so in this case we've got a secure key, and that says very strongly, I'm a member of this node map, I'm a client node and I belong here. You perhaps don't actually need the network identifier in there, because the NID, we explored this earlier, you can spoof it. If I've got root, I can make up whatever I want about what my IP address is. And if I have the SSK, then by definition I've already got a strong form of auth. So to be honest, it would have helped us quite a lot if we didn't need to put those NIDs in. We wouldn't have had to write a queuing system to sort all this stuff out. We did, as I think the Kerberos chat earlier mentioned this, we've seen some race condition type stuff with GSS in general. I think more usage in the wild would probably help sort that out. So the more people using it, the better from our perspective. It would have been good if Lustre had an API. Actually, it does have an API, and it's very, very good. It just didn't do the stuff that we were doing here. So you've got to listen to me talk for 50 minutes about writing one. And the other thing was just a note of thanks, which was that DDN, Rich is here somewhere, very kindly gave us a virtual appliance. I know if you're using open source Lustre, which I suspect most of you are, this is probably a non-issue for you. But for us, being able to replicate a test environment to write software was really important. We probably couldn't have done it if we hadn't been given this thing. It's a lightweight Vagrant Exascaler, just a virtual DDN. You spin it up on your laptop. Works great. So I'm very, very grateful to DDN Professional Services for that. That's it. Thank you very much for listening. I hope you enjoy the rest of the afternoon.